Hello, everyone. Tonight we're going on a journey, not a frantic high-speed one, but a slow, deliberate drift. We won't be traveling through outer space, though we'll get there eventually. Instead, we're going to descend very slowly and very, very carefully into the warm, glowing depths of Earth's hidden heart. We're here to talk about volcanoes, yes, but not in a way that will make you sit bolt upright in bed. We're here to find the stillness, the poetry, and the deep geological patience in a world that likes to let off a little steam from time to time. The Earth you see is not just a ball of rock. It's a layered sphere, a massive ancient cosmic onion. And tonight, we're going to peel back those layers one by one to see what lies beneath. Now a gentle warning, and I say this with a knowing little smile, while this journey is designed to soothe your mind and guide you toward a gentle sleep, I can't promise it won't accidentally pique your curiosity. If you find yourself sitting up in bed at 3 a.m. whispering, "Wait, did they just say the Earth's mantle is like a very thick, reluctant syrup?" Then I suppose I've done my job a little too well. But don't worry. If you're still wide awake at the end, at least you'll have a few fun scientific facts tucked under your pillow. But for now, let's begin our descent. First, let's settle in. Fluff your pillows. Adjust your blankets. Find that perfect, just right spot on the couch or in your bed. Let your breath slow. Let your thoughts wander without urgency. Just relax and listen. Now, before you go and watch, please take a moment to like and subscribe to this video, but only if you truly enjoy what I do. And if you're feeling extra cozy, I'd love to know where you are in the world right now and what time it is where you are. Feel free to leave a comment below. I read them like bedtime stories. Ready? Let's begin. Imagine, if you will, the Earth as this giant layered sphere. At the very center is the inner core, a solid ball of mostly iron and nickel. It's about as hot as the surface of the sun, but the immense pressure from all the layers above keeps it from melting. This is the ultimate forge, the unmoving heart of our world. We won't linger there. It's far too toasty. Surrounding that is the outer core, a swirling sea of molten metal, so vast it's almost beyond comprehension. This isn't just a pool of liquid. It's a dynamic, churning ocean of iron that generates our planet's magnetic field, shielding us from the harsh solar winds. It's the silent, invisible force field that makes life on Earth possible, and it's a stunning example of how something so deeply hidden can have such a profound and visible impact on our lives. The academic debate surrounding the exact origins of this magnetic field and how it has fluctuated throughout geological history is a captivating field of study. Some scholars propose it's a self-sustaining dynamo, while others point to ancient thermal or chemical forces. It's a beautiful, ongoing argument in the scientific community, one that reminds us that even the very foundation of our existence is full of fascinating questions. Above the outer core, we find the mantle. This is where things get truly interesting for our story. It's a colossal region of hot, dense rock that makes up about 84% of Earth's volume. Now here's where we get to the poetry. The mantle is solid rock, but over geological time scales, we're talking millions upon millions of years it flows. Not like water, not even like honey. Think of it as an extremely thick and reluctant syrup, a kind of slow-motion liquid putty that deforms and moves under pressure. This slow churning motion is what we call mantle convection, and it's the engine that drives everything we're about to discuss. It's a process so slow, you could sit and watch for 1,000 lifetimes and not see a single millimeter of movement. Yet, it's powerful enough to move continents. The fact that solid rock can flow given enough time and pressure is one of the most beautiful and counterintuitive truths of geology. It's a testament to the idea that patience on a planetary scale can create immense change. Now let's drift outward to the very top. Floating atop this slow-churning mantle is the crust, our home turf. If the Earth were an apple, the crust would be its paper-thin peel. It's a brittle, cold, and fractured shell, broken into giant puzzle pieces we call tectonic plates. These plates shift, bump, and grind against each other, sometimes giving us earthquakes, sometimes forming towering mountain ranges, and often, when the conditions are just right, birthing volcanoes. A little-known fact is that the oceanic crust is much thinner and denser than the continental crust. It's a crucial detail that plays a huge role in how volcanoes are formed. Think of it like this: the continental plates are thicker and lighter, like a big dry sponge floating on the water, while the oceanic plates are thinner and heavier, more like a wet, dense piece of wood. When they collide, the heavier plate almost always loses, sinking back into the mantle in a process called subduction. That's a key piece of the puzzle we'll come back to later. For a long time, the concept of plate tectonics itself was a huge mystery. The ancient Greek philosophers, including Aristotle, believed in a static, unchanging Earth. This belief persisted for centuries. It was only in the early 20th century that the theory of continental drift was proposed by Alfred Wegener. But it was largely dismissed at the time due to a lack of a plausible mechanism. It wasn't until the 1960s, with the discovery of mid-ocean ridges and evidence of seafloor spreading, that the idea of plate tectonics was finally accepted. This historical struggle for a revolutionary idea to be taken seriously is a quiet reminder that even in science, our perspectives are shaped by what we already believe to be true. The journey continues, and you find yourself suspended, floating just below the surface where the crust meets the mantle. It's here that the story of volcanoes truly begins. They don't just appear out of thin air like a party trick gone wrong. They grow, they form, they build themselves up patiently. Over time, shaped by forces both violent and subtle, every bubbling lava fountain, every ash-spewing mountain, and every quietly steaming vent is the surface expression of something deeper, something ancient, something that has been happening for billions of years. A popular historical belief was that volcanoes were the work of angry gods or mythological creatures. The ancient Romans believed Mount Etna was the forge of Vulcan, the god of fire. In a way, they were right about the fire, but the source was a bit more geological. The earliest humans, with no scientific instruments to explain what they saw, had no other way to make sense of the ground rumbling and fire spilling from a mountain's top. It was a terrifying, yet beautiful mystery. As you drift here, in this liminal space between the crust and the mantle, you'll begin to notice something special: molten rock. We call it magma. This isn't just rock that's gotten a little warm. It's rock that has melted, and it's a key ingredient in our story. Magma forms in several ways, but the most common is when the rock in the mantle gets hot enough, or when pressure decreases in just the right way, or when it gets infused with a bit of water. A fascinating little-known fact is that water, which seems so cool and calming to us, can actually act as a catalyst for melting rock. When water seeps into the mantle, it lowers the melting point of the surrounding rock, allowing it to turn to magma at a lower temperature. It's a bit like adding salt to ice to make it melt faster. It's a quiet, subtle process, but it is responsible for some of the most dramatic and explosive volcanoes on the planet. Once formed, this molten material, which is lighter and less dense than the solid rock around it, begins to rise. Think of it as a bubble in a thick milkshake, slowly, persistently making its way toward the surface. This rising magma doesn't just shoot straight up. It often collects in reservoirs beneath the surface called magma chambers. Think of these as underground storage tanks, vast caverns and spongy zones filled with pressurized molten rock quietly waiting. It's a place where different batches of magma can mix, where crystals can form, and where gases can build up, all while the pressure mounts. It's the volcano's hidden heart, its backstage, and its secret. Sometimes when the pressure builds too high, or when a pathway opens to the surface, the magma erupts. And that, my friends, is when our quiet, slow, and beautiful story becomes a bit less quiet. The dramatic and sudden appearance of a new island or a volcanic peak, a seemingly spontaneous event, is in fact the culmination of a process that has been brewing for centuries or even millennia deep below our feet. The idea that all of this power comes from a slow, steady increase in pressure is perhaps one of the most soothing truths in all of geology. There are no sudden cosmic punches, just a relentless gentle pushing from within. It's a slow-motion rebellion, a protest by the planet against being contained. You can almost hear the soft, rumbling grumble. As you float here, you'll begin to appreciate the scale. The Earth's crust, which feels so solid and unmoving beneath our feet, is in a state of constant slow-motion ballet. Continents drift, oceans grow, and mountains are born, all thanks to the invisible quiet forces we are now exploring. It's a humbling thought, isn't it? That the very ground we stand on, the thing we consider the epitome of solid and stable, is just the thin, fragile skin on a slow-boiling pot. But don't let that make you nervous. Instead, let it be a source of wonder. The same forces that create a volcano are the forces that create new land, new oceans, and new life. It's a cycle of destruction and creation, and we are lucky enough to be a tiny part of it. So for now, just relax. Let your thoughts drift. We're here suspended just below the surface where the heat begins and the mystery takes hold. Feel the gentle warmth. Listen for the silent hum of the mantle. We'll descend a little deeper in our next chapter. The dance of the tectonic plates is a slow, elegant waltz. At divergent boundaries where plates pull apart, magma rises to fill the gap. These are the most common type of volcanoes on the planet, quietly building new seafloor beneath the oceans. They are the ultimate builders, creating more land inch by inch than all the other volcanoes combined. Then you have convergent boundaries where one plate dives beneath another. These are the locations of the most explosive and unpredictable volcanoes, the ones that often ring the Pacific Ocean in a region ominously known as the Ring of Fire. This subducting plate carries water and minerals deep into the mantle, lowering the melting point of the rock above it and creating the volatile gas-rich magma that leads to violent eruptions. And then there are hotspots, plumes of heat that rise from deep within the mantle, burning through the crust like a blowtorch. These are not tied to plate boundaries and can create chains of volcanoes as the tectonic plate moves over them like footprints across the ocean floor. The Hawaiian Islands are a classic example, a living demonstration of a plate moving slowly but surely over a stationary source of immense heat. There's a little-known detail about these plates that's both fascinating and slightly ridiculous. Imagine you have a tiny invisible flea. Now imagine that flea is walking along the ground. That's roughly the speed at which some of these plates move. For instance, the Pacific Plate is moving at a rate of about 7 to 10 centimeters per year, or roughly the speed your fingernails grow. So the ground beneath your feet is moving, but it's doing so with a patience that is almost cosmic in its scope. The academic debate surrounding the exact mechanisms of plate tectonics and how they started is still very much ongoing. For decades, geologists have been debating whether it's a process driven primarily by ridge push, where new crust pushes plates apart, or slab pull, where old crust sinking into the mantle pulls the plates down. It's a beautiful ongoing argument in the scientific community, one that reminds us that even the most accepted scientific theories are still being refined and explored. The fact that the Earth has this incredible self-regulating system of creation and destruction, driven by a syrup-like mantle and thin, brittle plates, is a profound and comforting thought. It means our planet is not static. It is alive. It breathes, it shifts, and it remakes itself constantly, without haste, without rest. The volcanoes we'll explore in the coming parts are not random acts of planetary violence. They are the punctuation marks in a long, beautiful, and ongoing sentence written in fire and stone. They are the moments when all that slow, quiet pressure finally finds an outlet, a chance to express itself in a magnificent display of raw power. And tonight, as you drift towards sleep, you are right there witnessing the very beginning of that story. So breathe deeply. Let your muscles relax. We're in a safe place far from the heat, but close enough to feel its gentle pull. We'll continue this journey in the next chapter. You are suspended now, not quite in the mantle, but in the twilight zone, just above it, where the heat begins to assert itself, and the rock hums with a silent, simmering energy. We've established that the Earth is a cosmic onion, a layered sphere of elegant simplicity, and that the story of a volcano begins not with a bang, but with a very, very slow burn deep beneath the surface. Now we drift a little closer to the heart of the matter, to the secret birthplace of all that fiery power, the magma chamber. Imagine this space not as a great open cavern filled with bubbling, fiery lava, as you might see in a cartoon. There are no floating skulls or skeletal dragons down here, thankfully. Instead, think of it as a spongy, seething blend of solid rock and molten material. It's more of a plumbing system than a lake, a complex network of fissures, pockets and channels where the rising molten rock or magma begins to collect. This is the volcano's hidden heart. It's backstage where all the drama is prepared, long before the curtain ever rises on the surface. So how does this magma get here? We know it rises because it's lighter than the surrounding rock, but what triggers the melting in the first place? It's a question that has captivated geologists and philosophers for centuries. Ancient scholars like Pliny the Elder, who famously chronicled the eruption of Mount Vesuvius in 79 AD, observed the physical violence of a volcano, but had no way to explain its origin. They saw the symptom, not the cause. It took millennia of patient observation and scientific discovery to peel back this layer of the cosmic onion. One historical theory, which seems quite quaint now, was that magma was simply the result of fire burning deep within the Earth's belly like a giant underground furnace. While there is certainly heat, the process is far more nuanced, more poetic. The truth is, rock melts in three primary ways, and all of them are a testament to the quiet, subtle forces that shape our world. The first and most common is decompression melting. This sounds complicated, but it's actually a beautiful, simple concept. Rock, like all matter, has a melting point that is directly related to pressure. At the immense pressures of the deep mantle, rock can remain solid even at temperatures of over 1500 degrees Celsius. But when that same rock begins to rise toward the surface, slowly, patiently, like that bubble in a milkshake, we talked about, the pressure on it decreases. And when the pressure drops quickly enough, the rock doesn't have time to cool down. It just starts to melt, forming magma. This is what happens at mid-ocean ridges, where tectonic plates are pulling apart, allowing rock from the mantle to rise to fill the void. It's a bit like taking a lid off a pot of boiling water. The steam, the magma, rushes out. This is the Earth exhaling very slowly and very persistently, creating new ocean crust in the process. The second method is a bit more sneaky, a quiet magic trick performed in the depths. It's called flux melting. This occurs at subduction zones, those places we mentioned, where one tectonic plate, usually a dense oceanic one, dives beneath another. As the oceanic plate descends, it carries with it water and other volatile compounds trapped in the rock and sediments. Now we normally think of water as a cooling agent, but here it plays a different role. When that water is released into the superheated surrounding mantle, it acts like a catalyst, a kind of geological antifreeze. It lowers the melting point of the rock, allowing it to turn to magma at a lower temperature than it normally would. This is why subduction zones are responsible for some of the most explosive and gas-rich volcanoes on Earth. That little bit of water seeping into the planet's heart is the key ingredient that turns a quiet simmer into a potential storm. A little-known fact is that this process also helps explain the famous ring of fire, the string of volcanoes that encircles the Pacific Ocean. The ring is essentially a giant subduction zone where the Pacific plate is constantly being recycled beneath the surrounding continental plates. It's a beautiful and slightly moody dance of fire and water. Finally, there's a method that is less common, but no less elegant: heat transfer melting. This is a bit like melting an ice cube by dropping a hot coal on it. When a very hot batch of magma intrudes into cooler surrounding rock, it can transfer enough heat to cause that rock to melt as well. This usually happens near existing magma chambers, where one type of magma heats up the rocks around it, potentially triggering even more melting and mixing. It's a process of self-perpetuation, a positive feedback loop that can make a volcanic system even more complex and unpredictable. The academic debate surrounding the exact proportions of each melting mechanism at different types of volcanoes is still a point of fascinating discussion. Some geologists argue that the relative importance of each process varies wildly depending on the specific tectonic setting, while others seek a more universal model. It's a reminder that even when we understand the core principles, the specific details can be a source of endless inquiry. As you drift closer to the magma chamber, you begin to see the results of these processes. The chamber itself isn't a singular space. It's a complex dynamic system. Magma doesn't just sit there, it evolves. Over time, it can undergo a process called fractional crystallization, where different minerals solidify out of the melt at different temperatures, altering the composition of the remaining liquid. It's a bit like making a reduction sauce. What's left becomes thicker, richer, and, in the case of magma, sometimes more explosive. A little-known fact about these chambers is that they can also be home to a process called magma mixing, where new batches of hotter, less viscous magma can intrude into a cooler, more evolved magma chamber. The result is a kind of geological cocktail, often with bubbles, and this can be the final trigger that destabilizes the system and causes an eruption. The atmosphere in this subterranean realm is one of immense pressure and profound patience. The magma here might wait for years, centuries, or even millennia before an eruption. It's a timeless pause, a quiet meditation on immense power. For a human, 100 years is a lifetime. For a volcano, it's a moment, a geological hiccup. It reminds you that we are operating on two vastly different timescales. The one you live in full of hurried moments and ticking clocks, and the one the planet lives in, measured in eons in the slow, relentless flow of rock. And it's a comfort, isn't it? To know that the forces that shape our world are not hurried, not frantic. They are methodical, patient, and deeply rooted in the fundamental laws of physics and chemistry. The magma chamber is the ultimate example of this. It is a place of potential energy, of stored power, a silent promise waiting to be fulfilled. And as you drift away from its warm glow, you can feel the subtle shift in the rock around you, a slow, gentle pressure building waiting for its cue. The story of a volcano's birth is a story of quiet power, a story of stillness before the storm, and a story that reminds us that some of the most dramatic events in nature begin in the deepest, most tranquil places. So now, as you drift further away, leaving the warmth behind, you can feel the rock around you solid and cool once more. The chamber is a memory now, a warm spot in the back of your mind. But its existence reminds you that every mountain has a history, and every eruption has a secret heart. In our next chapter, we will continue to explore the architecture of these giants. You are now floating suspended in the cool, solid rock of the Earth's crust. The warmth of the magma chamber is a memory, a gentle hum in the distance. We've journeyed through the planet's layered heart and witnessed the slow, patient birth of magma. Now we begin our gentle ascent toward the surface, and as we do, we encounter the very architecture of a volcano itself. This isn't just a random pile of rocks. It's a masterpiece of geological engineering, and its anatomy can tell us a great deal about what lies beneath. Think of a volcano as a kind of organic plumbing system. At the base, you have the magma chamber, which we now know is a complex reservoir of molten rock. From there, the magma travels upward through a conduit, a central pipe, or a series of fissures that act as a volcanic highway toward the surface. At the top, it often emerges through a central vent, or sometimes multiple smaller side vents. The eruption itself forms a crater at the summit, and if the volcano has a particularly dramatic blowout, that crater can collapse into a wide depression known as a caldera. Calderas can be massive, spanning several miles across, and they often fill with water to become serene and deceptively peaceful crater lakes. This basic structure, however, comes in many flavors. Just like people, volcanoes have their own distinct personalities and physical forms, shaped by the type of magma they're fed and the style of their eruptions. Let's drift and examine a few of the most common types. First, there are the shield volcanoes. These are the gentle giants of the volcanic world. They are wide with gently sloping sides that resemble a warrior's shield laid flat on the ground. They are built almost entirely from runny, low-viscosity lava flows that spread far and wide before cooling. Think of Mauna Loa in Hawaii, one of the largest volcanoes on Earth. Its slopes are so gradual, you might not even realize you're on a mountain until you reach the summit. Their eruptions are typically non-explosive and effusive, with lava gently oozing out like syrup on a warm pancake. For the ancient Polynesians of Hawaii, these volcanoes were not fearsome monsters, but living gods. They built their homes and their farms on the fertile volcanic slopes, living in a peaceful coexisting relationship with Pele, the goddess of fire. It's a beautiful historical truth that reminds us that humans have long found a way to not just survive, but to thrive in the shadow of these magnificent peaks. Next, you have the stratovolcanoes, also known as composite volcanoes. These are the classic postcard-style volcanoes, tall, steep, and dramatic, often snow-capped and majestic. Think of Mount Rainier in Washington State or Mount Fuji in Japan. These volcanoes are formed from alternating layers of lava ash and rock fragments building up over time into towering peaks. Their beauty, however, belies their danger. Their magma is typically thicker and more viscous, trapping gases and leading to explosive and unpredictable eruptions. The presence of these towering, moody peaks has long shaped the cultures of the people who live near them, woven into their myths, their art, and their daily lives. A little-known fact about these beautiful peaks is that they are often formed at subduction zones, those places where one plate dives beneath another, which, as we discussed, creates gas-rich and volatile magma. And then there are the cinder cone volcanoes, the overachievers of the volcanic world. They are small, steep, and formed almost entirely from pyroclastic debris, a fancy term for the bits of rock and ash that get hurled into the air during an eruption and then rain back down to Earth. Cinder cones may not be large, but what they lack in size, they make up for in enthusiasm. Their eruptions are brief but powerful, and they are often found in groups or on the flanks of larger volcanoes. A common misconception is that these are just miniature versions of stratovolcanoes, but their formation and composition are entirely different. The academic debate surrounding the longevity of cinder cones is still an open question. While many are single eruption events that build up over a few weeks or months, some geological evidence suggests that certain cinder cones may have had multiple eruptive episodes over time, a topic that continues to fuel scholarly discussions. As you continue your slow ascent, you realize that not all volcanoes play by the rules. There are complex volcanoes, fissure volcanoes, submarine volcanoes, and even ice-covered volcanoes hidden beneath glaciers. Some lie dormant for thousands of years, while others grumble and sputter on a regular basis. Each one tells a different story shaped by its environment, its chemistry, and its unique personality. Some are quiet and consistent, like those in Iceland, politely letting out lava with minimal fuss. Others are loud, explosive, and utterly unpredictable, prone to tantrums that can blanket cities in ash or send shockwaves around the world. A fun, slightly ridiculous historical detail is that ancient Romans, when they saw a volcano erupt, believed it was the sound of the god Vulcan forging weapons for the gods. They would throw offerings into the crater to appease him, which, sounds like a bad idea with the lava and all. You can just imagine the conversation. "Hey, Marcus, maybe don't throw your best toga into the volcano. It's a bit of a fire hazard." It's a hilarious, if slightly tragic thought. Beneath all that drama lies a simple truth. Volcanoes are driven by pressure and density. Magma wants to rise because it is less dense than the rock around it. When it finds a path upward, it takes it. If that path is blocked, pressure builds, and when the lid finally pops, well, that's when we get an eruption. Interestingly, not all magma even makes it to the surface. Sometimes it stalls in the crust and cools underground, forming what geologists call an intrusion. These hardened bodies of rock like batholiths and laccoliths can later be exposed by erosion, forming dramatic features, like Yosemite's El Capitan or the Black Hills of South Dakota. It's like a volcano that never quite made it to the party, but left a stunning gift anyway. The academic debate surrounding the formation of these intrusions is still vibrant, with geologists arguing over whether they form as a single massive intrusion or through a series of smaller repeated events. The fact that these seemingly solid, unmoving mountains are actually the result of a slow, patient, and sometimes explosive process that reaches deep into the Earth's core is a powerful and humbling thought. You can't look at a volcano the same way again. It isn't just a scenic backdrop. It's the tip of a much larger and much more fascinating iceberg. It's a story of pressure, of heat, and of ancient fire, all expressed in the shape of a mountain. A historical fact you might not know is that the very first geological survey of a volcano was done on Mount Etna, with scientists studying its history to try and predict its behavior. These early attempts at scientific understanding, while crude by today's standards, laid the groundwork for the modern field of volcanology. As you continue to drift upward, the air gets cooler, the pressure eases, and you can begin to see the first hints of light from the surface. The world of molten rock is now behind you, but its legacy is all around. The solid rock you are passing through, the very ground you will soon stand on, was once just as hot, just as fluid, and just as full of secrets. It's a beautiful thought, a reminder that everything solid was once in flux. We have moved through the anatomy of a volcano, from its hidden heart to its visible peak. In the next part of our journey, we will take a step back and look at the molten material that fuels it all, the magma itself. You are now leaving the elegant structure of the mountain and entering the complex chemistry of its soul. So breathe deeply. You're almost at the surface, and don't worry, there's a nice, cool, non-explosive place to land just ahead. You are now floating, not in the heart of a mountain, but in the molten heart of the matter itself. You've left the architecture of the volcano behind and are now suspended within the very substance that gives it life, magma. This isn't just molten rock. It's a story of heat, pressure, chemistry, and time, a fluid and seething library of information that holds all the secrets of the volcano's past and future. Understanding magma is like listening to the planet's deepest whisper, a monologue delivered in a language of elements and temperature. The primary ingredient that determines a magma's personality is silica. It's a key chemical compound, and its concentration influences everything from the magma's viscosity to its tendency to explode. Think of it like a thickening agent in a sauce. The more silica, the thicker and stickier the magma becomes. The less silica, the more fluid and fast-moving it is. This is a crucial concept, a simple truth that separates the gentle glowing lava flows of a Hawaiian volcano from the catastrophic explosions of a stratovolcano. There are three main categories of magma, and each one is a character in our story. First, you have basaltic magma. This is the most common type, typically found at mid-ocean ridges and hotspots like Hawaii. It has the lowest silica content, usually between 45% and 55%. It's also the hottest, scorching 1,000 to 1 to 200 degrees Celsius. Because of its low silica content, basaltic magma is very runny, like a thin hot syrup. This means that gases can escape easily, and it tends to flow rather than explode. Basaltic magma produces those beautiful glowing rivers of lava you see slowly oozing across the ground. A historical fact you might not know is that the ancient Hawaiian people who lived with these gentle eruptions had specific names for different types of basaltic lava. They called the smooth, ropey lava pahoeho, and the chunky jagged lava AA, which is an incredibly fitting name when you try to walk across it. The academic debate surrounding the exact mechanisms of how these two types of lava form from the same magma is still a point of discussion, with some geologists arguing it's about the speed of flow and others pointing to gas content. Next, we have andesitic magma. This one has a moderate amount of silica, about 55% to 65%. It's thicker and cooler than basaltic magma and is usually formed at subduction zones. Andesitic magma is a bit more moody. It doesn't flow as easily and has a tendency to trap gases. This combination can lead to more dramatic and explosive eruptions and the formation of those tall, steep stratovolcanoes we discussed earlier. Think of it as magma, with a bit of a temper, sometimes calm, sometimes testy, and often unpredictable. The Roman philosopher Pliny the Younger, who witnessed the eruption of Mount Vesuvius in 79 AD, described the andesitic eruption in his famous letters, providing one of the first and most detailed historical accounts of such an event. He described a towering column of gas and ash, shaped like an Italian pine tree, a beautiful and terrifying image that has captivated historians for centuries. Finally, we have rhyolitic magma. This is the diva of the magma world. With more than 65% silica, it is thick, sticky, and full of gas. It doesn't flow, it creeps, it seethes, and when it erupts, it tends to do so with impressive flair. Rhyolitic eruptions can be truly catastrophic, launching massive amounts of ash into the sky and forming huge calderas. Thankfully, they are also relatively rare, which is perhaps for the best. A little-known fact about rhyolitic magma is that when it cools, it can form obsidian, a natural volcanic glass. Ancient cultures, including Native American tribes in the Pacific Northwest, valued obsidian for its sharp edges and used it to create tools and arrowheads. The irony is beautiful. A substance born of such violent potential can become a tool for creation. A joke, if you will. Why did the rhyolitic magma break up with the basaltic magma? Because it said, "You're too runny, and I need a little more commitment." Now let's talk about the pressure. It's the driving force, the quiet engine behind all of this. As magma rises toward the surface, the pressure decreases and gases that were dissolved under high pressure, mostly water vapor, carbon dioxide, and sulfur gases, begin to expand. It's exactly like opening a can of soda. As long as the can is sealed, everything is calm. But once you pop the top, especially if you've shaken it, those bubbles rapidly expand and escape. In magma, if those bubbles build up too quickly and can't escape due to the high viscosity of the magma, they can cause a dramatic explosive eruption. The ancient Greek philosophers who loved to theorize about the elements would have had a field day with this concept. The idea that something as simple as a trapped gas could cause such immense power would have been the ultimate example of their elemental theories. You're drifting now through the essence of these magmas, a swirling, colorful blend of temperature and chemistry. You can feel the distinct character of each one, the gentle, languid heat of the basalt, the sticky tension of the andesite, and the restless, seething energy of the rhyolite. They all have their own story, their own rhythm. The academic debate surrounding the exact temperatures and compositions of magma and how they evolve over time is still a very active area of research. Geologists use a process called geothermobarometry to estimate the temperatures and pressures at which a magma crystallized. But this is a complex science that still has many unanswered questions. The idea is to use the mineral composition of a rock to work backward and figure out the conditions of its formation. It's a bit like being a detective looking at the clues left behind to solve a very, very old mystery. A historical truth is that the observation of magma's behavior, particularly its viscosity, led to some of the first attempts to classify volcanoes. Early volcanologists noticed the difference between the broad shield-shaped volcanoes that produced runny lava and the steep cone-shaped volcanoes that produced explosive ash. This simple observation laid the groundwork for modern volcanology, showing that a volcano's shape is directly linked to the chemistry of the magma it produces. Now, as you drift out of this elemental soup, you can feel the molecules around you beginning to settle. The temperature begins to drop ever so slightly. The story of magma is not just about its eruption. It's about its quiet existence, its patient waiting, and the slow, inexorable forces that drive it. It's a reminder that even the most chaotic-seeming events in nature are governed by elegant and simple rules. You have now journeyed through the soul of the volcano. In the next part, we will witness the full spectrum of its performance, from the quietest whisper to the loudest roar. So breathe deeply. The curtain is about to rise. You are now floating, poised to witness the climax of our story. We've journeyed through the Earth's layers, explored the anatomy of the mountain, and felt the distinct personalities of different magmas. Now, we arrive at the performance itself, the eruption. This isn't a single event, but a wide and varied palette of expressions, a full emotional range from a gentle whisper to an explosive scream. The style of the eruption, as we now know, is dictated by the magma's chemistry, temperature, and most importantly, the pressure of trapped gases. Let's begin with the most polite of all eruptions, the Hawaiian eruption. These are the quiet, continuous performers named after the volcanoes of Hawaii, particularly Mauna Loa and Kahlawea. The magma is basaltic, hot and runny with a low silica content. This means the gases can escape easily without much fuss. The result is a mesmerizing spectacle of glowing lava fountains and long-flowing rivers of molten rock that creep across the landscape like a slow molten syrup. These eruptions are often safe enough to watch from a distance, and they are oddly peaceful, like watching a giant fiery river flow with serene power. A historical truth you might not know is that ancient Hawaiians who lived with these gentle giants would often engage in rituals to honor Pele, the goddess of volcanoes, believing that her gentle eruptions were a sign of her contentment. They understood that these volcanoes, while powerful, were also creators of new land, and their relationship with them was one of respect and awe, not fear. Next, we have the Strombolian eruption, named after the volcano Stromboli off the coast of Italy. These are a bit more enthusiastic than their Hawaiian counterparts. They feature short, explosive bursts of lava and gas, often at regular intervals, like a geological hiccup. The magma is slightly thicker, which causes the gas to build up and burst in a shower of glowing volcanic bombs and ash. They're moderately explosive, but not typically destructive unless you're standing in the wrong place at the wrong time. A little-known fact is that Stromboli has been in near-constant eruption for over 2,000 years, earning it the nickname Lighthouse of the Mediterranean for its frequent, fiery displays. The academic debate surrounding the regularity of these eruptions is a fascinating one, with scientists still trying to fully understand the intricate plumbing system that allows for such a consistent rhythm of explosions. Now let's turn to the more dramatic performers, starting with the Vulcanian eruption. These are short but powerful explosions of ash, rock, and gas, named after the island of Volcano, Italy. The magma is thicker than in a Strombolian eruption, trapping more gas and leading to a more violent release. These can produce shock waves, ash clouds, and most dangerously pyroclastic flows, a term we'll get to in a moment. These eruptions are the equivalent of a sudden angry outburst after a long, quiet pause. The sound of a Vulcanian eruption is said to be like the roar of a cannon, a sound that would certainly wake you up. A fun, slightly irreverent thought. It's as if the volcano has finally had enough and decided to throw everything it had at the wall just to make a point. Finally, we have the truly apocalyptic, the Plinian eruption, named after Pliny the Younger, who documented the eruption of Mount Vesuvius in 79 AD. These are the big ones, characterized by a towering column of ash and gas that can reach the stratosphere, intense explosions, and widespread devastation. The magma is typically rhyolitic, thick, sticky, and gas-rich, making it the most volatile of all. When it erupts, it is with a force that can flatten forests and bury entire cities in minutes. The historical truth of the Vesuvius eruption is a haunting reminder of this power. Pliny the Younger's letters describe the eruption column as resembling a pine tree, a plume of smoke and ash that rose into the sky and then spread out, raining down debris on the cities of Pompeii and Herculaneum. The academic debate surrounding the exact timing and nature of the pyroclastic flows that buried the cities is a rich and ongoing area of archaeological and geological research, speaking of which we must touch on pyroclastic flows. If lava flows are the slow-glowing rivers of a volcano, pyroclastic flows are their hyperactive, terrifying cousins. They are fast-moving avalanches of superheated gas ash and volcanic debris that race down the sides of the volcano at speeds of up to several hundred miles per hour. They are incredibly dangerous, incinerating everything in their path. The city of Pompeii was buried by one as was St. Pierre on the island of Martinique in the early 1900s. It's a chilling thought that something so destructive can move so fast. A little-known fact about these flows is that they can also be formed by the collapse of an eruption column. When a Plinian column of ash and gas loses its upward momentum, it can collapse and race down the mountain, creating an unstoppable force. An eruption doesn't just go sideways, it also goes up. Volcanic ash, tiny particles of pulverized rock, can rise tens of miles into the sky. Once there, it gets carried by wind, often traveling thousands of miles before settling back down. In large quantities, ash can clog airplane engines, damage crops, and turn sunny days into twilight. The 2010 eruption of Eyjafjallajökull in Iceland is a modern example of this. It was a relatively modest eruption, but its ash plume grounded flights across Europe for days. A fun, if slightly inconvenient reminder that a small volcano can have a big impact on our interconnected world. The academic debate surrounding the exact factors that trigger the sudden shift from a gentle eruption to an explosive one is still a vibrant area of research. Volcanologists use a variety of tools, including seismic sensors, gas monitors, and satellite data to try and predict these events, but the complexity of a volcano's inner workings means that a full certain prediction is often impossible. The final trigger might be something as subtle as a new batch of magma intruding into a chamber or a sudden change in gas content. It's a beautiful, humbling field of study, one that requires both data and a deep sense of respect for the unknown. As you drift away from this spectacle, you can feel the energy of the eruption fading. The loud roar has become a quiet hiss. The chaotic dance of ash and gas is now a gentle plume of steam. You have witnessed the full palette of a volcano's power, from its quietest moments of creation to its most dramatic acts of destruction. You now understand that a volcano is not just a mountain. It is a living, breathing entity with a complex and varied emotional life. In the next part of our journey, we will explore the lasting legacy of these dramatic events. The fire is gone, but the story is not over. We will look at the scars and masterpieces that are left behind, the landscapes born of fire and pressure that are now a testament to the Earth's boundless creativity. So breathe deeply. The show is over, but the quiet beauty is just beginning. You are now floating not in the heart of a volcano, but gently above the world it left behind. The heat is gone, the roar is a memory, and you are surrounded by the silence of a landscape shaped by fire. It's easy to think of a volcano as a purely destructive force, but as you drift over this terrain, you begin to see that it is also a powerful artist, a sculptor on a planetary scale. These landscapes are the scars and masterpieces of Earth's fiery past, a living testament to the paradox of destruction and creation. Let's begin by looking down upon a caldera. We discussed these briefly earlier, but seeing one from this perspective is a whole other experience. A caldera is a massive crater-like depression formed when a volcano's magma chamber empties in a colossal eruption and the ground above collapses in on itself. Some calderas are so large that entire cities could fit inside. A perfect example is Crater Lake in Oregon. It formed about 7,700 years ago after Mount Mazama erupted and then collapsed. Over time, the caldera filled with rain and snowmelt, creating one of the clearest and deepest lakes in the world. Its deep blue color is almost hypnotic, a calm reflective surface born from violent origins. It's a beautiful historical truth that the local Klamath Native American tribes viewed the lake and its surroundings as a sacred place, a solemn reminder of the power of nature. They would avoid looking at the lake, directly believing it was a portal to the spirit world. A powerful testament to the awe that these landscapes have inspired in humans for millennia. Then there are the lava flows. These aren't just barren black fields. They are intricate tapestries of rock, full of texture and form. In Hawaii, you'll often find Pasoho lava, which is smooth, ropey, and shiny like fresh taffy. It flows slowly and cools into surfaces that are deceptively soft-looking, but are actually quite hard underfoot. A fun, slightly mischievous thought: imagine trying to explain the difference between Pahoho and its counterpart, Aa, the chunky, jagged kind, to a geologist from another planet. So one is like a very wrinkled, thick blanket, and the other is like a pile of broken dinner plates. Got it. The academic debate surrounding the precise physical conditions that cause a single type of magma to form either Pahoho or Aa is still an active area of research, with geologists arguing over the role of flow speed, gas content, and even the slope of the land. But lava flows can also take a different path entirely downward. Lava tubes form when the surface of a lava flow cools and hardens, while the molten lava underneath continues to flow. Eventually, the lava drains away, leaving behind long, hollow tunnels. These lava tubes can stretch for miles beneath the surface, some large enough to walk through. A little-known fact is that ancient Polynesians in Hawaii used these tubes for shelter and even for sacred rituals. These subterranean tunnels are a hidden network, a quiet echo of the fiery rivers that once flowed through them. As you drift over these landscapes, you can see other geothermal wonders. Geysers are hot springs under pressure. Water seeps deep into the earth, heats up near magma, and then explodes back to the surface as steam. Old Faithful in Yellowstone is the most famous example, erupting predictably every 90 minutes or so, like a very hot, very punctual tea kettle. Then there are fumaroles openings in the ground that vent steam and gas, often smelling strongly of rotten eggs, thanks to hydrogen sulfide. You can almost hear the earth sighing, a warm, smelly breath, a joke, if you will. What do you call a volcano with a cold? A runny nose. The academic debate surrounding the exact mechanisms that trigger a geyser's eruption is still ongoing, with scientists trying to model the complex interplay of water heat and pressure in the deep plumbing system. A historical truth is that the indigenous people of North America, particularly the tribes in the Yellowstone area, had a deep understanding of these geothermal features. They used the hot springs for warmth and healing, and revered the geysers as powerful spirits, integrating them into their myths and cultural practices. This indigenous knowledge, passed down through generations, predates any formal scientific study of the area, and is a testament to how closely early humans observed and understood the natural world around them. The volcanic islands themselves are a testament to this creative power. Entire landmasses formed from the accumulation of eruptive material on the seafloor until they poke above the ocean surface. The Hawaiian Islands are a perfect example, a chain of volcanic peaks formed as the Pacific Plate slowly drifted over a stationary hotspot. Each island in the chain is a bit older and more eroded than the last, moving northwestward like geological dominoes. This slow-motion island assembly line has been operating for millions of years, and it's still going. The next island in the chain, named Loihi, is currently growing underwater and might breach the surface in a few tens of thousands of years. It's a beautiful thought, a promise of new land in a distant future. Another little-known fact about these landscapes is that they are incredibly fertile. After the initial devastation of an eruption, life tends to return with surprising speed. The ash and lava break down into nutrient-rich soils that support lush vegetation. Crops like coffee grapes and bananas thrive in volcanic regions, which is why some of the most famous wine-growing areas in the world, including parts of Italy and Chile, owe their richness to ancient eruptions. Volcanic soil is essentially nature's multivitamin for plants, and it shows. As you drift over a black sand beach, you see yet another beautiful paradox. These beaches are formed when hot lava flows into the ocean, cools rapidly, and shatters into tiny fragments. Over time, these fragments are ground down by waves into smooth, jet-black grains of sand. The result is a beach that looks like it was sculpted from ink, stunning eerie, and a vivid reminder that even destruction can lead to a haunting kind of beauty. You have now seen the full cycle of a volcanic landscape, from its destructive birth to its serene, beautiful old age. The mountains, the lakes, the fields, and the beaches are all a part of this story. A story of Earth's relentless and patient creativity. In the next part of our journey, we will descend once more, this time to a different kind of landscape, the human one. We will explore how people have learned to not only live with these giants, but to thrive in their shadow, a testament to the resilience of both nature and humanity. So breathe deeply. The ground below you is solid, but its story is one of a liquid heart. You are now floating, hovering just above the fertile green slopes of a volcanic peak. The air is cool and crisp, but you can feel the warmth rising from the soil below, a gentle, nurturing heat. We have seen the volcano as a force of nature, a magnificent and sometimes terrifying entity. But here in this serene landscape, we begin to see it through a new lens, as a life giver, a provider, a quiet partner to humanity. For thousands of years, people have chosen to live not just near these mountains, but directly on their slopes, a choice that seems counterintuitive until you understand the deep, paradoxical relationship between humans and these geological giants. The most compelling reason, as you can see, is the soil. Volcanic soil, or andesol, is one of the most fertile types of soil on the planet. When lava and ash break down over time, they release a rich mix of minerals like potassium, phosphorus, calcium, and magnesium. This natural buffet supports everything from vineyards to rice paddies to banana groves. This is why you'll find some of the world's most productive agricultural regions in places that have been touched by fire. A historical fact you might not know is that the ancient Romans farmed the rich volcanic soils around Mount Vesuvius for centuries, cultivating grapes, olives, and wheat that were renowned for their quality. It was a trade-off, a life of abundance in the shadow of a sleeping titan, a testament to how, even in the face of immense power, humanity seeks to find a way to thrive. You can almost hear the soft rustle of leaves in the vineyards on the slopes of Mount Etna in Sicily, where grapes grown in the mineral-rich soil produce wines with a unique spicy character. Or the bustling activity in the rice paddies surrounding Mount Merapi in Indonesia, a volcano that is one of the most active in the world yet, whose presence provides the very foundation for life and sustenance for the local communities. A little-known fact is that volcanic ash itself, while destructive in an eruption, is incredibly beneficial to soil. It's a natural fertilizer, and a thin layer of ash can dramatically improve crop yields for years to come. This is why some farmers in volcanic regions will even welcome small, non-destructive eruptions, seeing them as a blessing rather than a curse. But the gifts of a volcano are not just agricultural. As you drift over these landscapes, you can see evidence of other resources being put to use. Geothermal energy is a prime example. In places like Iceland, which sits atop a volcanic hotspot and a mid-ocean ridge, this natural warmth is harnessed to provide electricity and hot water for entire towns. Pipes run under streets to keep them ice-free in the winter, and homes are heated by the natural warmth of the earth. It's efficient, renewable, and remarkably low in carbon emissions. A joke, if you will. How does a geologist warm their house? They just turn on the geothermal. The academic debate surrounding the exact origin of the deep water in some of these hot springs, whether it is entirely from rainfall or from a more complex mix of magmatic and meteoric sources, is a fascinating area of hydrogeological study. The hot springs themselves are another major draw both for their therapeutic benefits and their scenic beauty. People travel from all over the world to soak in mineral-rich pools heated by magma far below. In Japan, these onsen are an important part of the culture, a place for relaxation and contemplation. In New Zealand, geothermal areas like Rotorua offer not just a chance to relax, but also a glimpse of geysers and bubbling mud pots. These are living examples of how a volcano, even in its quiet moments, can provide comfort and wonder. A historical truth you might not know is that many ancient civilizations built their settlements around geothermal features. The city of Bath in England, for instance, was founded by the Romans who built elaborate public baths around the city's natural hot springs, believing in their healing properties. It's a clear example of how humans have been drawn to the warmth and power of the earth for millennia long before we had a scientific explanation for it. The cultural ties that bind people to these magnificent peaks are also a powerful force. In Naples, Italy, Vesuvius looms as both a guardian and a warning, an ever-present part of the city's identity. People have learned to live with it, to respect its moods, and to prepare for its potential anger. On the island of Java in Indonesia, volcanoes are part of daily life and religious practice. They are prayed to, studied, and climbed for recreation. In Hawaii, Pele, the goddess of volcanoes, is a revered and complex figure, both a creator and a destroyer. These cultural connections add a layer of meaning to the geological activity. The volcano isn't just a mountain, it's part of the story of who the people are. A little-known fact is that the ancient Hawaiian chant, E Ho Mai, is a traditional request for knowledge and inspiration from the natural world, often performed in the presence of volcanic landscapes, a direct communication with the power of the land. Of course, living near a volcano comes with an understanding of the risk. It requires a blend of practicality, optimism, and perhaps a touch of defiance. For some, the danger is manageable. They monitor the mountain, stay informed, and have evacuation plans. But for others, there is a deep psychological connection. It's the thrill of living on the edge of coexisting with a force of nature that operates on a different time scale. It's the beauty of the landscape, the dramatic mountains, the steam-filled valleys, the black sand beaches that makes the risk worthwhile. The academic debate surrounding the psychological motivations of people who live in high-risk volcanic zones is an ongoing area of sociological and anthropological research, with scholars trying to understand the complex interplay of cultural ties, economic necessity, and perceived risk. As you drift away from these thriving communities, you can see that the relationship between humans and volcanoes is not one of simple fear. It is a story of resilience, a tale of learning to live with and even be enriched by the magnificent power of the earth. The volcano provides the soil, the energy, and a sense of place. In return, humanity provides respect, patience, and a willingness to rebuild. It is a quiet, ongoing conversation between a species and a planet, a dialogue of fire and faith. The presence of volcanoes also has a powerful effect on the human imagination and our cultural stories. Myths and legends from around the world are filled with tales of fiery peaks inhabited by gods or monsters, from the Greek god Hephaestus to the Hawaiian goddess Pele. These stories are a way for humanity to make sense of the overwhelming power of nature, to give a face to a force that is beyond our control. A little-known fact is that the ancient Greek philosopher Empedocles, believing that the universe was made of 4 elements, fire, air, water, and earth, is said to have jumped into the crater of Mount Etna to prove his immortality. He did not, and his hubris became a cautionary tale for centuries. The academic debate surrounding this story is still a topic of historical study, with scholars questioning whether the legend is fact or fiction, a powerful metaphor for human folly. But even without the myths, volcanoes continue to inspire. The dramatic sunsets caused by volcanic ash, the eerie glow of lava at night, and the bizarre shapes of volcanic rock have long been subjects of art and poetry. Artists from J.M.W. Turner to Edvard Munch were inspired by the vibrant otherworldly colors of a volcanic sky. The eruption of Krakatoa in 1883, for example, caused spectacular sunsets around the globe for years, and many of the crimson and gold skies in Munch's paintings, including The Scream, are thought to be inspired by these post-eruption sunsets. It is a beautiful irony that a destructive force could create something so visually stunning and emotionally powerful. A joke, if you will. What do you call a painter who lives near a volcano? A landscape artist with a flair for the dramatic. Even in modern times, the relationship continues. The town of Hilo on the Big Island of Hawaii has been partially buried by lava flows from Kilauea multiple times. But the residents always return, rebuilding on top of the new land or finding new ways to coexist with the slow, persistent flow. The same is true for the communities around Mount Fuji in Japan and Mount Etna in Italy, where the mountains are both a source of pride and a constant, gentle reminder of their place in the natural world. The resilience of life in these environments is also a powerful lesson. After a major eruption, the barren lava fields slowly, patiently come back to life. Pioneer species like lichens and mosses are the first to arrive, breaking down the rock and creating the first fragile layer of soil. Then come the grasses, shrubs, and eventually a forest. This process, called primary succession, is a beautiful example of nature's boundless creativity. It shows that even in the most desolate landscapes, given time, patience, and just the right combination of sunlight and microbes, something green will always find a way to grow again. So as you drift away from these living, breathing landscapes, you can feel the warmth of the soil, the hum of the geothermal energy, and the quiet resilience of the people who have chosen to call these places home. You can appreciate that a volcano is not just a geological feature, but a character in a much larger story, a story of give and take, of destruction and creation, and of a deep and abiding connection between a species and a planet. We have seen the Earth as a living, breathing entity. In our next chapter, we will leave the Earth behind entirely and journey into the cosmos to see that this volcanic story is not just our own, but a tale that echoes throughout the universe. So breathe deeply. The ground below you is full of life, a testament to the fact that even after the fire, something beautiful always grows. You are now floating, and the Earth is a small blue marble below you. Its continents are faint, its oceans a soft azure, and its volcanoes are tiny, unmoving blemishes on its surface. We have seen the Earth's fiery heart, but now we're going on a journey far, far away into the cosmic silence, for we are about to discover a profound and beautiful truth. Volcanism is not an Earth-exclusive phenomenon. In fact, our entire solar system is a volcanic playground, a sprawling cosmic museum of fiery peaks and icy geysers, each telling a story of a planet's secret life. Let's begin right here in our cosmic backyard. The moon, that serene and silver orb that has captured human imagination for millennia, was once a far more dramatic place. It may look like a pockmarked, unchanging world now, but much of its surface was shaped by ancient volcanic activity. Those dark patches you can see with the naked eye, known as lunar Maria Latin for seas, are vast basaltic plains formed by lava flows billions of years ago. A historical truth is that early astronomers, with their simple telescopes, mistook these smooth, dark areas for oceans, hence the name. The academic debate surrounding the exact timing and cause of these ancient eruptions is still a subject of intense study, with some scientists arguing that they were triggered by large asteroid impacts that fractured the lunar crust. Today, the moon is volcanically dead, a geologically quiet world, but its pockmarked face is a monument to its fiery past. A little-known fact is that some of the lunar Maria contain tiny hollow tubes that are essentially ancient collapsed lava tubes, much like the ones we discussed on Earth. These tubes are of particular interest to future space explorers, as they could serve as natural shielded shelters from cosmic radiation, a very practical legacy of an ancient volcanic past. From the silent stillness of the moon, let's jump to somewhere far more dramatic, Io, one of Jupiter's largest moons. Io is, without exaggeration, the most volcanically active body in the entire solar system. It's a world that looks like it was painted by a psychedelic fever dream, all yellows, oranges, and reds. But Io's strange surface isn't just for show. It's covered with hundreds of volcanoes, some of which are actively erupting right now, spewing plumes of molten sulfur, hundreds of miles into space. Unlike Earth, Io's volcanic activity isn't powered by internal heat from radioactive decay. Instead, it's driven by tidal forces. Io is caught in a gravitational tug-of-war between Jupiter and its neighboring moons. This constant gravitational squeezing causes Io's interior to flex, stretch, and heat up, a process known as tidal heating. It's a bit like repeatedly bending a paperclip until it gets hot only on a planetary scale. A fun, slightly ridiculous thought: Io is basically the solar system's most overworked stress ball. The academic debate surrounding the exact composition of the plumes and the nature of Io's magma is still an active area of research, with some scientists arguing that the sulfur on the surface is a crust over a deep silicate magma ocean, a truly bizarre thought for our earthbound minds. Not to be outdone, Venus offers its own volcanic resume. Often called Earth's sister planet, Venus is a world wrapped in thick clouds and coated in mystery. We can't see its surface in visible light, but radar imaging from missions like NASA's Magellan spacecraft has revealed a land of rolling plains, highland plateaus, and an astonishing number of volcanoes. Estimates suggest that Venus has over 160,000 volcanoes, although most are small. A historical fact is that the Soviet Venera landers, which were the only spacecraft to successfully land on Venus's surface, only survived for a short time due to the extreme heat and pressure, but they did manage to send back a few photos showing a rocky, barren landscape that was almost certainly volcanic in origin. The question of whether Venus is still volcanically active is a fascinating one. A little-known fact is that some researchers believe that fluctuations in atmospheric sulfur dioxide levels and thermal anomalies on the surface hint at recent eruptions, a debate that is very much ongoing in the planetary science community. The academic debate surrounding the lack of plate tectonics on Venus is also a huge area of study. Geologists wonder why Venus, so similar in size and composition to Earth, lacks the dynamic plate system that drives our planet's geology. Some propose that Venus undergoes periodic, catastrophic resurfacing events where its entire crust melts and reforms at once, a terrifying and beautiful thought. Now let's head to the red planet Mars. Mars is home to the tallest volcano in the solar system, Olympus Mons. This towering giant stands nearly 22 kilometers high, about 2.5 times the height of Mount Everest. Its base is so wide that you could fit the entire state of Arizona inside it. Olympus Mons is a shield volcano formed by repeated highly fluid lava flows. But here's the twist: Mars doesn't have tectonic plates like Earth. That means a hotspot can keep feeding lava to the same location for millions of years, allowing volcanoes like Olympus Mons to grow to monumental proportions. A joke, if you will. Why did the Martian volcano get so big it just couldn't stop having growth spurts? The academic debate surrounding the timing of these ancient eruptions and whether there could be any intermittent low-level volcanic activity still occurring beneath its dusty crust is a very active area of research, with new data from orbiting missions constantly challenging our understanding. A little-known fact about Martian volcanoes is that they may have played a crucial role in shaping the planet's early climate. Volcanic eruptions would have released carbon dioxide and water vapor into the atmosphere, greenhouse gases that could have warmed the planet and allowed liquid water to exist on the surface. In this sense, a volcano's destructive power may have once created the conditions for life. Finally, we must talk about the strange, beautiful world of cryovolcanism. This phenomenon, or cold volcanism, is a little-known fact that completely changes our idea of what a volcano can be. On some of the distant icy moons of the outer solar system, volcanoes erupt with water ammonia or methane instead of molten rock. Take Enceladus, a small moon of Saturn. It's barely 500 kilometers across yet. It has a series of fractures at its south pole from which plumes of water vapor and ice particles shoot into space. A historical truth is that the Cassini spacecraft which flew through these plumes confirmed that they contain water salts and organic molecules, the building blocks of life. The academic debate surrounding the source of the heat that drives these eruptions is a fascinating one, with scientists pointing to tidal heating as the most likely culprit, a process that relies on the subtle push and pull of gravity to create a hidden, habitable ocean. You can also find cryovolcanism on Triton, a moon of Neptune. In the late 1980s, the Voyager 2 spacecraft captured images of dark geysers erupting from Triton's surface, reaching several kilometers into the sky. These eruptions are believed to involve nitrogen gas released when sunlight heats subsurface deposits of frozen nitrogen. Even Pluto, once demoted from planet status, but never from being interesting, may have cryovolcanoes. The New Horizons mission in 2015 revealed large dome-shaped mountains that look suspiciously like icy volcanoes, perhaps once belching out slushy ammonia lava under a pinkish sky. The sheer diversity of these volcanoes, from the fiery heat of Io to the icy cold of Pluto, is a beautiful testament to the elegance and creativity of the universe. You have now journeyed across billions of miles of cosmic space, and you have seen a universal truth. Volcanism is a fundamental process in shaping planetary bodies. It's a sign of internal energy, of active geology, and sometimes of habitability. Whether it's lava carving channels on Venus water erupting from Enceladus, or sulfur painting the surface of Io volcanic activity, helps to renew, reshape, and sometimes even sustain a world. It reminds us that even across billions of miles, planets and moons have their own pulses, their own tempers, and their own ways of breathing fire or ice into the universe. In our next chapter, we will return to Earth and explore the invisible but powerful ways a volcano can reach far beyond its slopes to affect the global climate. So breathe deeply. The cosmic story is a long one, but its lessons are all around us. You are now floating, and the Earth is a small blue marble below you once more. But this time, you are in the atmosphere, and you are not alone. You are suspended in a fine, almost invisible mist of dust and gas, a legacy of a distant eruption that has traveled far beyond its origin. We have seen how volcanoes can shape continents and even create new life, but now we explore their most far-reaching and subtle power, their ability to influence the global climate. It's a quiet atmospheric meditation on cause and effect, on how a mountain's outburst can send a shiver through the planet's weather systems. To understand this, we need to focus on one simple component of a volcanic eruption: sulfur dioxide. When a volcano erupts, it hurls vast quantities of gas into the atmosphere, including water vapor, carbon dioxide, and most importantly, for our story, sulfur dioxide. While all of these gases are important, sulfur dioxide is the real climate-altering culprit. When this gas reaches the upper layers of the atmosphere, the stratosphere, it reacts with water vapor to form tiny droplets of sulfuric acid. These droplets are called aerosols, and they are incredibly good at reflecting sunlight. Think of it like this. These aerosols form a delicate global-scale mirror that bounces a portion of the sun's energy back into space. Less sunlight reaching Earth's surface means cooler temperatures, at least for a little while. The cooling effect from a major volcanic eruption can last anywhere from a few months to several years, depending on how much sulfur dioxide is released and how high it reaches in the atmosphere. If the eruption is small or confined to the lower atmosphere, the particles quickly fall out of the sky as rain or ash. But if it's powerful enough to punch through to the stratosphere, typically over 10 kilometers up, those particles can linger, sometimes circling the globe multiple times, and producing sunsets that would make a painter weep with joy. A little-known fact is that these same aerosols can also contribute to the creation of beautiful, vibrant twilight colors, long after the sun has set, painting the sky with brilliant hues of crimson and gold. One of the most famous examples of volcanic climate influence occurred in 1815 when Mount Tambora in Indonesia erupted with astonishing force. This was not just your average bad day for a volcano. It was the most powerful eruption in recorded history. Tambora's eruption sent over 160 cubic kilometers of debris into the atmosphere and released massive amounts of sulfur dioxide. The following year, 1816, became known as the year without a summer. Across the northern hemisphere, temperatures dropped, snow fell in June in parts of New England. Frosts ruined crops well into July in Europe, and food shortages led to widespread famine and hardship. A historical truth is that this event, along with the disruption it caused, is said to have indirectly influenced the invention of the bicycle, as starving horses made travel difficult and expensive. The academic debate surrounding the exact global temperature drop and the specific impacts on regional weather patterns is still an active area of historical and climatological research. Tambora wasn't alone in its atmospheric influence. In 1883, another Indonesian titan, Krakatoa, erupted with similar ferocity. While the eruption itself was cataclysmic, its atmospheric effects were felt worldwide. The ash and aerosols from Krakatoa's eruption created vivid sunsets for years, inspiring artists and poets. A fun, slightly whimsical thought. It's as if the volcano, with its final breath, decided to paint a masterpiece for the entire planet to see. The academic debate surrounding the exact amount of sulfur dioxide released by Krakatoa is an ongoing area of study, with scientists using historical records and modern data to try and refine the numbers. More recently, the 1991 eruption of Mount Pinatubo in the Philippines provided a textbook example of volcanic climate influence, this time in the age of satellites and modern instrumentation. Pinatubo ejected approximately 20 million tons of sulfur dioxide into the stratosphere, forming a thick aerosol layer that reduced global temperatures by around half a degree Celsius for the next couple of years. This temporary cooling helped offset some of the global warming effects at the time, but it also confirmed what scientists had long suspected. Volcanic aerosols don't just cool the planet. They also affect precipitation patterns, leading to drier conditions in some regions and shifting the position of monsoon systems. A joke, if you will. Why did the volcano take a class on meteorology? It wanted to learn how to change the climate. It's a humbling thought, isn't it? That a single mountain in a single moment of immense pressure can have such a profound and far-reaching effect on the entire planet's atmosphere. It reminds us that Earth is not a static system, but a complex interconnected web of cause and effect, where a geological event in one corner of the world can ripple through every other part. A little-known fact is that the most effective volcanic cooling events are those that occur near the equator. Eruptions near the equator can spread aerosols more evenly across both the northern and southern hemispheres, amplifying their cooling effects. High-latitude eruptions, on the other hand, tend to keep their particles closer to home, affecting regional weather more than global climate. The academic debate surrounding the long-term effects of volcanic eruptions on climate and whether they have contributed to past ice ages or other major climate shifts is a complex and ongoing one. Geologists use ice cores from places like Antarctica and Greenland to study this. These frozen time capsules preserve layers of ash and sulfur from past eruptions, allowing researchers to track volcanic events going back thousands of years. By matching this data with other climate records, scientists can reconstruct how specific eruptions affected global temperatures and whether, piecing together the planet's long and fiery history, you are now drifting through a quiet atmospheric reminder of a volcano's power. The air is cool, the light is soft, and you can see the faint, beautiful haze that has traveled across oceans and continents to find you. It's a gentle, ethereal proof that nothing in this world is truly separate, and that even the smallest events can have the largest consequences. In our final chapter, we will bring our journey to a close, and you will descend once more, this time to the surface, where we will witness the ultimate paradox, how destruction gives way to creation, and how the fire within the earth is not a force of simple chaos, but a vital part of a grand and beautiful cycle of life. So breathe deeply. The journey is almost over, but the quiet beauty is just beginning. You are now floating not in the atmosphere, but gently descending toward the Earth's surface. The air is cool, the light is soft, and below you, a barren black landscape stretches out. This is the final act of our journey, a quiet meditation on the ultimate paradox of volcanoes. We have seen their power to destroy, to bury cities, to alter climates. But here on this silent, desolate plain of rock, we see their power to create. For after the smoke clears and the ground cools, something remarkable begins to happen. Life returns quietly at first, then steadily, persistently. This is the cycle of creation, a beautiful living truth etched into stone. To understand how this works, we must begin at the most basic level with the rock itself. When lava cools, it forms new rock, fresh, unweathered, and often barren. It doesn't look like much a jagged field of basalt, black and sharp. It feels inhospitable, and for a little while it is. But it won't stay that way for long. The first pioneers to move into these new volcanic landscapes aren't deer or birds, or even insects. They are microbes, tiny, tough, and not at all fussy about luxury. Certain types of bacteria and archaea can survive on bare rock, feeding off minerals, sunlight, or even gases released from the cooling ground. These microbes form biofilms and begin the slow, patient work of breaking down the rock, turning it into something more hospitable. In some cases, they can even fix nitrogen, an essential nutrient for life, which helps set the stage for more complex organisms to follow. A little-known fact is that these microbes are so resilient that some scientists believe they could be the first forms of life we discover on other planets. A beautiful thought that connects our own planet's history to the cosmic search for life. Next, come the lichens. These fascinating little life forms are actually partnerships between fungi and algae, or cyanobacteria. The fungus provides structure and moisture retention, while the algae or bacteria photosynthesize, producing food. Together, they cling to rock surfaces, slowly etching into the stone with weak acids. Over time, they help weather the rock into particles small enough to be considered soil. It's a long process. Think decades rather than days, but it's incredibly effective. Mosses and liverworts often follow, adding more green to the landscape. A historical truth is that early naturalists observing this process were mystified by how life could appear in such a barren place. They had no idea that a complex microscopic ecosystem was at work, a testament to the fact that even in the most desolate places, life finds a way. A joke, if you will. What did the lichen say to the rock? "You're not so tough, I'm already wearing you down." The academic debate surrounding the exact mechanisms of rock weathering by these early colonizers is still an active area of research, with scientists arguing over the relative importance of biological and chemical processes. As these early colonizers live, die, and decompose, they build up organic material, slowly creating a thin but viable layer of soil. Now the door is open for grasses, ferns, and small shrubs. With each generation, the soil deepens, nutrients accumulate, and the ecosystem gains complexity. In a few hundred years, that lifeless lava field may be a grassy plain. In 1,000 years, it could be a forest. This process is called primary succession, and volcanoes offer one of the clearest examples of it in action. It's a powerful and hopeful idea, the ultimate proof that even after total devastation, life not only returns, but thrives. One of the best studied examples of this comes from the island of Surtsey, off the southern coast of Iceland. In 1963, a submarine volcano erupted and built itself an island. Scientists immediately closed it off to the public, turning it into a living laboratory to see exactly how life would colonize a brand new landmass untouched by human influence. A historical truth is that the first arrivals were mosses and lichens, followed by seeds carried by ocean currents or deposited in bird droppings. The academic debate surrounding the exact order and timing of these early colonizers is still an active area of research as scientists continue to monitor the island's slow but steady progression. A little-known fact about Surtsey is that the first bird to nest on the island was a black guillemot in 1970, a simple event that marked a major milestone in the island's ecological development. As you land softly on the now solid ground, you can see the end result of this process all around you. The landscape, which was once a raw black scar, is now a vibrant tapestry of green. The volcano, which once roared with destructive fury, is now a quiet mountain, its slopes a testament to its creative power. A little-known fact is that volcanic soil, once it is formed, is incredibly fertile. It's a natural multivitamin for plants, and it's why many of the world's most famous agricultural regions are in volcanic areas. The volcanic soils of Italy, for example, have been cultivated for thousands of years, and the rich mineral-laced soil gives a unique flavor to the tomatoes, grapes, and olives grown there. It's a beautiful and delicious legacy of a volcanic past. The presence of a volcano also adds a layer of meaning to a landscape. A volcanic crater filled with a serene lake, a black sand beach at sunset, a steaming fumarole in the middle of a snowy field. These are places of wonder, places that remind us of the Earth's raw power and its boundless creativity. They inspire art, mythology, and science. They remind us of destruction, yes, but also of resilience, the forests that grow back, the animals that return, the people who rebuild. A historical truth is that the indigenous people of Hawaii, who live on one of the most volcanically active places on Earth, have a deep cultural connection to their volcanoes. They see them not as a threat, but as a living, breathing part of their history and their identity. The academic debate surrounding the ethical responsibilities of scientists studying these sacred places is a fascinating and ongoing one, a testament to the fact that science and culture are often deeply intertwined. And so we come to the end of our journey. We've wandered through molten hearts and frozen geysers, stood at the edge of craters, and peered into the dark oceans of distant moons. We've listened to the whispers of Earth's inner chambers and watched the sky grow strange under the influence of distant ash. From the very first spark of life to the sculpting of new lands, volcanoes have proven themselves to be both destroyers and creators. Fierce, majestic, and often misunderstood. All of this, and yet we've barely scratched the surface. The earth beneath our feet is still moving, still shifting, still breathing heat and pressure into every crack and fold. Volcanoes are not just relics of a wild past. They are part of our present. They shape our landscapes, influence our climate, and remind us sometimes quite loudly that this planet is alive. So as you lie back now, maybe with eyelids growing heavy and thoughts drifting like lazy plumes of steam, I'll gently ask what I asked at the beginning. Where are you listening from? What time is it there? Midnight 2 in the morning. Perhaps you're on the other side of the world, where the sun is just starting to rise. Either way, I hope you found this time to be relaxing, fascinating, and just engaging enough to carry you to the edge of sleep without dragging you into the heart of a lava lake. And if I've kept you awake with tales of boiling seas and icy volcanoes on Saturn's moons, well, at least you've learned something. If you've enjoyed this journey with the Midnight Muse, I'd be so grateful if you could leave a like, tap that subscribe button, and let me know in the comments where you're listening from. It's always a joy to know who's out there drifting through science and sleep with me. Sweet dreams, and may your inner earth stay peacefully dormant tonight.